This conference will now be recorded.
Hi, everybody. Sometimes I get questions, certain questions that are asked over and over again. And one of them is, what's the difference between the standard deviation and the standard error? So I'm going to try to show you kind of quickly what it is. It's easier than writing it out, I think, for me. And hopefully you'll get a little better comprehension, or hopefully a lot better after we're done with this. We're going to look at some slides here. Then I'm going to show you some formulas, and then I'm going to show you something like a demonstration. And hopefully we can do this in maybe 15 minutes or so. So let's get started. First of all, basically on these slides, what I want you to understand is we use statistics to make guesses at things. Okay, so we will have, there's a population, often you'll hear population and sample. Okay, a population is a great, usually typically something that's very big that we can't possibly find the value of every single element in that population. Let's say like the age of everybody in the United States. It would be very hard to get a record of everybody's age in the United States and then find an average, okay? So what we will do is pull a sample, and it's a much smaller piece of the big population. And if we do the sample pooling right, basically if we get a random sample and we follow some other rules, we should get a good representation of a very large population by using a smaller sample. Okay, so basically we're guessing with statistics. Okay, so a lot of times in statistics you're going to be looking for a mean or maybe coefficients in a regression, some kind of estimate, right? You're going to be estimating a parameter that's in the population. So really, even though we're guessing at what the mean is or a coefficient is or something like that, we're really wanting to have a good idea of how much variability is in our measurement. We might get a good sample of the ages of everybody in the population, but how good is our estimate, right? We just get a number, but the variance and standard deviations and standard errors and things like that help us understand how widely spread the data is in the population from our sample. Okay, so a lot of times you'll hear things called variability, uncertainty, error, and noise, and these are all the same thing. Okay, we really want to get a beat on that, and so that's what we need to do with our standard deviations and standard errors and our variance. Okay, so here's some reasons that we need statistics, okay? And the reason why you don't want to look at everything in a population also. Say your population is a lot of light bulbs, right? Because you have, many lots of light bulbs, but say you have one big lot of maybe, I don't know, 2,000 light bulbs or something like that. Well, here we go, 20,000 light bulbs, okay? And you want to know the average life of those light bulbs. Well, you can't destroy them all, because if you do, you'll have none to sell, right? So what you're going to do is pull a random sample, burn those ones out, and then it should give you a good estimate of how what the average is for all 20,000 or whatever you have left out of the 20, right? Um, Otherwise, the other things we might want to do is, as I was saying, like the age of every person in the United States. Well, perhaps we want to know the proportion of redheads. Okay, so what proportion of people are redheaded, say in the United States? Well, I'm not going to look at everybody's hair color. Okay, so what I will do is pick a representative and random sample, if I can, from a great big list or from the population, and see if I can get a good estimate, okay, of what it would be. Okay, so you know, sometimes you just can't look at everything. Okay, and that's where we have statistics. So statistics are guesses at the truth. If you knew the truth, you wouldn't need statistics. You would just go and burn out all those light bulbs, or you would look at every single number. People that use big data, typically that is your population, and you are looking at the whole population. So it's kind of different things would apply in big data. You actually are looking at the population means and such and getting confidence intervals. Probably aren't really necessary if you have the population, because you will know what the average is, right? But in statistics, we're assuming we can't pull from the huge population. We're just getting a representative sample, and we're using those to estimate what the truth is. Okay, so think of population and parameters belonging to the population. Okay, these are the big things we never know the truth about, but we're going to be guessing at with our statistics. Okay, so we'll pull a sample from the population, and And then we're going to derive a statistic that's going to be representative of that parameter in the population, okay? And then on our statistics, since we're not going to be exact because we are not pulling out of the whole population, so there will be some error in our estimates, some variability, we'll build a confidence interval around that statistic. And it'll tell us, usually we do a 95% confidence interval, and we can guess at a number, say the average, and then we'll build this range around it. And we'll say, yes, we guess this particular average. However, we can be 95% confident that the true average is somewhere in between this range of numbers. And this so we will be using the standard error to determine that confidence interval. I'm not really going to do confidence intervals today. I'll just do the difference between standard deviations and standard errors. But I do have videos on the YouTube channel where you can, I do show you how to do confidence intervals. Okay, so here's a little graphic. Over here we have population, parameter, and a truth, okay? So these are the things we're never really going to know, but we're going to pull a sample from the population, okay, smaller piece of the population. We're going to make it representative, which typically means random, okay? We're going to measure a statistic from that sample, and we're going to estimate it for that parameter. And then of course we have a very good guess. So we're going to put that confidence interval around our good guess as a just a little cushion. Okay, another thing that's nice to know is I will show you a little bit of notation in a minute, mathematical notation. Parameters are typically represented by Greek notation, and statistics are typically represented by the ABCs, so I always joke that one of the top 10 reasons for becoming a statistician is that I've always wanted to learn the Greek alphabet. As you can see, what we'll be looking at today, well, as you can see, some of these they're a little bit off. Here's a P, it's the proportion of population data, but a little p is a proportion of sample data. So yes, P is a Latin character, but typically then they'll capitalize them. N is the population size, but little n is the sample you're pulling out of the big population. Today we're going to be looking at the N's, okay, and we're also going to be looking at sigmas and the S's. So the variance of the population data will be sigma squared. The standard deviation is sigma, okay? And then those are for the population, right? Things we'll never know. And the things we're guessing at are the variance of the sample data, which is S squared. And then if we take the square root of S squared, we will get the standard deviation of the sample, okay? And then basically all we do is divide this sample standard deviation by the square root of our sample size, and that gives us a standard error. I'll show you some formulas. Let's go ahead and get those formulas up now. Here we go. So I'll talk a little bit. Today we're going to a little bit about this from the normal distribution point of view. You can get a mean and a variance by and standard deviations and variances and means and things like that from any type of distribution, really. But I think it's easier to show these concepts with the normal distribution. And that's going to be that nice bell shape. A lot of things go to that bell shape, a lot of continuous data. So like ages, heights, weights, things like that, measurements of many kinds will actually tend towards a normal distribution. And a lot of other distributions, if you pull a large enough sample, will also go to normal. Binomials, hypergeometrics, Poisson will go to normal if you pull a large enough sample. So it's kind of nice to work with that. And the reason we like to is because of the symmetry of it, okay? So standard deviation and variance are both determined by, in our case, we're going to be using the mean of a group of numbers, okay? The mean is the average of the group, and the variance is going to measure the average degree to which each number is different from the mean, okay? So we're going to have that center, that mean, and then we're going to look and see how wide of a variance or variability we have around that means of all our data, okay? So the extent of the variance correlates to the size of the overall range of numbers. So if you have a very wide range of numbers around your mean, around your average, you're going to have a very large variance. And then if you have a small range around it, you're going to have a smaller variance. And it's just kind of an indication of how spread out your data is. So the variance it's the average of the squared differences from the mean. Okay, so basically what you're going to do is, let me kind of pull, well, I'll show you a little picture here. It might be a little bit more useful. We'll look at this data a little bit more in a minute. But I'm going to say this is a population. We have about 9,000 data points, 9,500 data points. They're ages of, it's actually of people who had neck, throat, and neck and head cancer for about 5 years of time. But it was a big database, like 10,000 records. Okay, so here is what I was talking about, that nice bell-shaped distribution, see? So our average is going to be in here somewhere where the measurements are piling up the most. So here's the number of measurements, okay? So we had some people, and here's our age. So we had some people that were very young that had cancer and were treated, and some people that were rather old, okay? But on average, our average is 56.58 in years, and our standard deviation is 11.407 years. Okay, what we have to do though is, since we have an average here, and we're taking for our formula is that we're going to subtract this mean value of 56.58 from all the other values that we got for age, you will end up with some negative values, right? So say if we had this person down here that was a 20-year-old, okay, down in this area, and we subtracted 56.58 from it, well, there you go, you're 36, a negative 36 or so. So if we were to do that part of the equation, let's go back to our, if we were to do this and sum them up without squaring them, then we could basically get a 0, right, for our variance. Although looking at that, of course, it's not 0. Distance is never 0, right? And we're looking at distances from the mean. So we want to account for these also being of a magnitude that's not going to zero out the positive ones, right? So that's why we square. Okay, so what we're going to do is we're going to take each of our actual values, subtract that 56 years or so from that, then we're going to square it, okay? And then we're going to sum them all up. So we're going to take this, subtract the average, take the data point, subtract the average, square it, and then sum them up, okay? And then we're going to divide that answer by n, by the, it would actually be the population in this case, right? Because this is the variance for the population, so it would be the known population. And then we're going to take the square root of it to make the standard deviation. Okay, so this is our variance in here. Okay, and then if this is going to be our sigma squared, and then if we square root it, we're going to get this. Okay, so if we have a sample, so we can do it now, if we pulled a sample out of that big population, we should be able to estimate what the population was, okay? And here we're going to have from our little data points that we collected from our first data point up until the last one in our sample, the small n, okay? And then we're going to subtract our sample mean, which is x bar, from each of our little data points that we collected, and then we're going to square it. We're going to do the same thing, but we're just going to do it with actual data now, right? And then we're going to subtract 1 from our sample size, our little n. That's going to give us our standard deviation. If we don't take the square root of it, then that's our variance. Our variance is going to be inside here. So our variance is in here, and then the square root of the variance is the standard deviation. And the reason we do that is because we had to square these for the variance, right? We had to square to get an actual number. Well, when you look at the variance is going to be huge. It's going to really be, because it's the sum of all these squared values, both the negative and positive ones. So you'll usually have this huge variance that really doesn't give you any indication of the spread of the data. For example, let's go back and look at our population here. I have some data. I'm calling this a population, right? We're going to be pulling samples out of it, and I'll show you how it goes with this. But I'm calling this the population, so I changed this to parameters. So our true mean is 56.58. Standard deviation, see how small it is compared to the variance? Our variance is 130.112. Okay, well, we look at that and that doesn't really give us an indication of anything, but the standard deviation does. If we take the square root of the 130, right, 0.112, we square root that, we'll get 11.41 or so. That's one standard deviation. And you probably know that what is it? There's a certain amount of data that goes with each little standard deviation, right? About 60 some percent will be within plus or minus one standard deviation from the mean. About 75% or so within plus or minus two standard deviations, and about 99% of your data should be within plus or minus three standard deviations from the mean. So what we did is we just squared that variance. It brought this number back down to something we can use for measurement, because this is also in years. So the standard deviation is also in years now, again. So we can say our average is 56.58 years, but a standard deviation is about 11 years. So if I was to multiply this 11.407 times 3, so 3 times 11.407, it's about 34.22. So what I could do is I could take that 34, add it to the 56. That means 90 should probably be my highest value, because that's 3 standard deviations higher. Or I can subtract it, 56 minus the 34 or so, and that's about 22. So I would be expecting my data to be somewhere between 22 and 90, okay, to actually be within plus or minus 3 standard deviations from this mean. Okay, now if I look down here, I can see my minimum was 18 and my maximum was 88. Okay, so I have a couple little low lying guys here. I'm using SPSS here for this output, and I'll show you how to run it in a minute, but it really gives you a lot of information, which is great. But it's basically, I should probably have some outliers in these lower ranges. So if I go down here and look at the box plot, see down here, these are the 18-year-olds, right? Because I should be starting around 22 or so if I want to be within -3 standard deviations from that 56 years of age. So I have some outliers in here, but I'm not going to worry about it too much, because there's, out of 10,000, we have 1, 2, I don't know, 6 or 7 maybe. So I'm not going to worry about these guys too much, because it does look pretty normal. It looks really good. There's also this normal QQ plot. If your data points are lined up on this diagonal here, you're looking pretty good for a normal distribution. Also, if you look, where is it? Oh, this Kolmogorov-Smirnov test, or there's also a Shapiro-Wilk test. Don't trust them too much when you get to have about 50 or so more data points, because they're very sensitive to large sample size. So this is basically telling me, since it's significant, that it's not a normal distribution. But my gosh, look at that histogram, look at that QQ plot. It looks normal enough to me. I'm going to say it is, okay? Another way you can tell is if your mean is close to your median, because your median is supposed to be the true middle, right? So the true middle is at 56. And so my mean estimated a little high, 56.58. And that could be because we had a couple older people up here. Okay, and I kind of pulled it up a little bit. Again, they're very close in value. I would go ahead and I wouldn't even worry about transforming this data. I would just use it raw, just like it is. All right, so I think now we have a good idea of variability, and that standard deviation is the square root of the variance, right? And kind of how they're computed. I think I needed to show you one more thing here, and that was the standard error of the mean. Okay, so the standard error would be the standard error of this little X bar, okay? Our mean from the sample, okay, is going to be our sample standard deviation divided by the square root of our sample size, okay? So the standard error of the mean is going to describe how precise the mean of the sample is versus the true mean of the population. So what that's really going to do is your population is, the mean estimate is the estimate of the mean of the population. Your standard deviation is, the spread of the data in the sample, but as far as a population would go. But your standard error of the mean is like, how far is the mean you guessed at? How far is that from the true mean of the population? And this is why we build our confidence intervals with the standard error of the mean. Okay, so I'm going to run a couple little things here in our numbers. So I have my data set. I'm going to go ahead and pull that up real quick. All I did was age, and like I said, what I had about 10,000 records. So let's go ahead, and I'm just going to pull out of here. I'm going to select some cases, okay? So I'm going to show you how this changes. Let's go ahead and select maybe 10%. Okay, so I want to pull a random sample. We had, what, about 10,000 cases, so let's pull about 1,000 of them. So I'm going to say just approximately 10% of all cases, and I'm going to hit continue, and we're going to hit OK. And then I'm going to go ahead and I have a filter variable now. So this is the filters, the ones are what were chosen. And as you can see, it crossed out these guys that aren't chosen. So what I want to do is click data. I want to split my file. I want to compare groups. I'm going to organize it by my variable here, the filter variable. I'm going to hit OK. Now what I'm going to do is I'm going to go ahead and go into the descriptives. I'm going to go into Explore. This is in SPSS, which is it's very nice. I picked this. I picked age. Okay. And then over here, I want to display both statistics and plots. I'm going to go in statistics. I'm going to ask for 95% confidence interval, outliers. I want to see if there's anything outlying. Plots, I'm going to choose a histogram. It gives you the option of stem and leaf, but I like histogram. I'll ask for normality and the test of normality, and then the options. I'm just going to go ahead and say, it doesn't matter on this. I'll just keep it pairwise. We're only looking at one variable. Okay, so here's what I got. We have here, it gave me the approximately 10% of the cases. So here we pulled a random sample of 923. Okay, records. Okay, so here's our statistics, and now I'm also going to have some standard errors here. So my average was 56.11, and that was versus, what was it before? It was 56.58, right? So that's pretty darn close, right? With a sample of 100, I got pretty darn close. And then my standard error in the sample was 11.41 or so, right? So let's go down in here and look again. So here I have 56.11. Okay, a little bit low, but gosh, still 56. 11.25. Okay, again, a little low, but not too bad. And then I have the standard error. Okay, so this tells me my estimate of the mean from that population. With 1,000, I got pretty darn close to it. Okay, also the standard deviation of that population, right? Got pretty darn close. And now I said, okay, well, I made a good guess. I made a guess on that average of 56.11, but my standard error, I could be plus or minus this. All I do with the standard error for the 95% confidence is I take this 0.370 and I add and subtract, or I multiply it by 1.96, and then I add or subtract whatever value I got from that 56.11, and that'll give me a good bead on the estimate. I don't really have writing tools, I don't think. Let me see here. So I would say, here we go, 1.96, excuse my writing, times 0.370. So let me go ahead and do that. 1.96 times 0.370 gives me 0.73. Okay. And now what I'm going to do is take this 0.73 and I'm going to add it to the 56.11. I'm going to subtract it from the 56.11, and that will give me this 95% confidence interval that's right here. Okay, so let's see, 56.11 minus 0.73, 55.38. Yeah, it's pretty close. I mean, it's rounding errors, okay? And then if I add that 0.73, I should get this 56.84. So this is what the standard error does. It tells me how close to the population mean am I, okay? But your standard deviation is going to tell you, the different on the how big the spread of the population itself is, right? As in terms of your ages. Okay, so this is actually it's kind of like doing this. It's like the standard deviation of your estimate, right? It's like, well, how off am I on my estimate? But this is like, how does your data look all together with your standard deviations? Okay, so that's with 1,000 records. So we did pretty good. We got very close. That confidence interval, if we can be 95% confident that the true value is in here somewhere, we're pretty good. Okay, now let's see if we do something a little bit smaller. If we do smaller, you're going to find with smaller samples, we're not going to get as good. Okay, so I'm going to go back in here to data again. I'm going to select cases. Now I'm going to say, let's see, oh, maybe I can erase this here. How do I erase this? Oh, I hope it's not here the whole time. Okay, well, we'll figure it out. Let's go ahead and move this down here. Okay, so now I want to say random sample of about, let's go 1%. Okay, that's still going to be pretty good, I'll bet you. And then we'll hit OK. And now our filter will be for the 1%. So let's go ahead and look at that. Descriptives, explore. I can just hit OK again. Okay, and here we go. Let's see if I can erase this. I have everything in here but eraser. Okay. There, erase. Yay, good. Okay, so now we have 105 that we pulled out of that 10,000 or so, 9,500 or so, right? So now we have 105. We estimated the mean to be 55.87. Our standard error is bigger now, 1.10, because we don't have as big of a sample. So we're going to be a little bit smaller, or a little bit larger. I'm sorry about that, a little bit larger on our standard error, which just means for our confidence interval is going to be more spread out. Now we can say we got an average of 55.9 or so, but we can be 95% confident that that true average is somewhere between about 53.7 and 58. Okay, so now we have a few years in there, right? Our minimum and maximum, still they're not looking so bad, our Kolmogorov-Smirnov test and our Shapiro-Wilk now, both are saying we have normality, because remember I said if they get about 50 or so, they'll say everything's non-normal. But let's go ahead and look at our histogram here. It looks okay. There's some low liars down here, right? But we know the population looks darn good. Our QQ plot, I'm not going to be worried about that at all. And again, like I said, if your mean and your median are close, we're doing pretty good. Now we're about 1 year off. Let's try it with something crazy. Let's just look at 3, okay? And then we'll be done. So let's go back into data, select cases, sample. I'm going to say I want to select exactly 3 cases from the first. How many did we have in our sample? Oh, I don't know, 9,400 something. Let's say, 9495. 9495. Okay, so I'm randomly selecting 3 from all of these. Okay, continue. Okay, and now let's go ahead and run it. Okay. So we have 3 records, okay? Now we got an age of 51.67, so we're actually off from the population. We're low, about 5 or so, right? Our standard error is much bigger, okay? We're going to multiply this by 1.96 and add or subtract it. So look at now how large our confidence interval is, 31.59 years up to 70. We can be 95% confident that the true mean is somewhere between 32 and 72 years. That's huge. That's kind of worthless, isn't it, whenever you pull such a small sample? Okay. Again, checking normality is going to be really hard to do with just 3 items, right? So it really didn't even test it here. The Shapiro-Wilk was tested and it said it looks okay. To look at the histogram, you'd have no idea. That doesn't look like much of anything, right? So, however, we do know this was what the population looked like, right? That's what we had as a population. So yeah, so hopefully that's helpful, and it gives you an idea of what we use the standard error for, what the standard deviation's for, and what the difference is. So again, the formulas kind of, once you do all this and you look at the formulas again, it kind of really gives you an idea. And then also there were some, let me pull that PowerPoint up again. Okay, you can look at some of these places to get some more information. Okay, here's the information for me. Please feel free to give me a call. My email's down here. Go check out my website. I have a lot of recordings and latest news and such. There's a newsletter you can sign up for so you get information about every week or so from me of things I come across in practice. So, but I hope you enjoyed this. And yes, thanks for watching and good luck. Okay, bye-bye.